Hello everyone, we are the team that have won the third place in the first videos in Parsing in the Wild Challenge. It's my honor to give a presentation here to introduce our work. I will introduce the whole work in 4 parts. First, I will briefly give some basic information about our team. Then I will focus on the network structure that we used as well as how we train the model. Finally, I will summarize our work, including the conclusion and some further progress direction. First is the base information part. Our team consists of 3 members from AI algorithm group of Xiaomi. We get the 3rd place in MIOU as well as the 2nd place in video consistency. Here's the leaderboard. We have submitted a technical report titled Semantic Segmentation of VSPW Dataset through Aggregation of Transformer Models. The archive address is shown as below. Next is our network structure. Here's an overview of our structure. We use 2 encoder-decoder model to separately perform segmentation on the same image. Both get a soft segmentation result. We perform a weighted summation on these 2 soft segmentation and then use an argmax operation to produce the final segmentation result. For the 2 encoder-decoder model, we choose transformer-based network as the backbone. We research SLTA results of transformer-based model and the CNN-based model on 2 datasets, namely ADE and Cityscapes. The results are collected from the website Papers with Code. We find that in ADE, transformer has much better performance and the combination of HRNet and OCRNet, which is one of the best CNN models in semantic segmentation. However, in Cityscapes, HRNet plus OCR stays to be the SLTA model. We think that this is caused by the scale of dataset, including the number of classes and the number of images in a dataset. Transform-based model may perform better than CNN in a large-scale dataset. So we choose Swing and the Swing Transformer and the Volo, which are both transformer models, as the backbone of our structure. The results show that they indeed show greater power than CNN. This table comes from the original paper of VSPW dataset, showing that CNN commonly achieves less than 40 MIOU. But in our experiment, which with transformer backbone, we can easily achieve more than 50 MIOU on both validation set and test set. Here's the detailed structure of Swing model. Swing transformer extracts the feature of an image through 4 stages of attention computing. We take output of the last 3 stages, resize them to the same size, and concave them to obtain a multi-scale feature. The feature is sent into OCRNet to get the soft segmentation map. The next is the structure of Volo model. First, the image goes through a shallow CNN to extract low-level information. Then, a liner layer is used to increase the feature channel and perform downsampling, which is the process of patch embedding. A few vision out local layers extract the high-level semantic information from the embedded feature. To increase the resolution, we use a UNet structure to aggregate the output of the shallow feature, the embedded feature, and the high-level feature. The aggregated feature is also sent into an OCRNet to get the segmentation result. So our final model structure is just like this. Then I will show how our models are trained. First, we separately train the Swing model and the Volo model with different training settings. After both models are trained well, we perform a model aggregation to further boost the performance. Here, the aggregation parameter gamma is set to a hyperparameter instead of a trainable parameter. We use 2 kinds of loss function in our training process. The first is based on pixel distribution. We count the number of pixels of each class in training set, marked as Ni. and μn as the average of ni. The weight is computed with this equation. The loss is revised with the weight based on the cross-entropy loss. The design principle is that for each pixel, if it is predicted wrongly, and either the ground truth class or the predicted class is a class with few pixels, then this error will greatly do harm to the MIOU. So the weight is set as the maximum between the weight of the ground truth and the predicted class. The second loss function we use is a confusion metric-based loss. It is used to fine-tune the model. When the model has been trained and get an acceptable performance, we compute the model's confusion matrix on validation set. This confusion matrix shows detailed information. For example, which two classes may be easily confused by the model. In this loss function, we give these classes higher weights so that the model can focus on easily confused samples. Let's see the detailed training setting. We use the default data augmentation in MM segmentation. Specifically, we apply multiscale with a resize ratio ranging from 0.5 to 2. We also apply a random crop. The crop size is set to the resolution 480 multiplied by 853, which is the most common image size that appears in VSPW dataset. In addition, we apply random color transform, including random brightness, random contrast, random saturation, and random hue transform. Apart from data augmentation, we use a DAMW optimizer, batch size 16, and linear learning rate update rule. For swing model, we train it with two stages. In the first stage, we use swing air as backbone. We train the model for a long period. We use pixel distribution based loss, warm-up strategy, and only VSPW dataset for training. Since the backbone loaded pre-trained model, we set the decoder's learning rate larger than the backbone. We fine-tune the model with the second stage for better performance. In this stage, training period is short. We deepen the backbone, use confusion metric-based loss, set encoder and decoder with the same learning rate, and add COCO dataset for training. For a VOLO model, we train the model with a quite small learning rate, pixel distribution based loss, and we use VSPW, ADE, and the cityscapes for training. When the training converges, we continue to train a few epochs and use the exponential moving average method to combine the saved weights for a better model parameter. Then is our inverse time method. We use a test time augmentation. For swing model, we apply multiscale and flip. For VOLO model, we find that the change of input size may do harm to the model performance, so we only apply the flip operation. Finally is the model aggregation. We apply a weighted summation on the output of swing and VOLO model. As a common choice, just set the aggregation parameter as 0.5 can bring great benefit. During the final stage of the challenge, we set gamma as 0.56 for the best result. This is our experiment result. We can see that our training setting have achieved obvious progress on the model's performance. Models trained with crop size 480 multiplied by 853 perform better than those with crop size 512 multiplied by 512. In addition, extra dataset and test time augmentation has benefited the performance of swing model. The UNet model structure and the method of weight average has increased the MIOU of VOLO model on test set. With both swing and VOLO model trained well, model aggregation brings further progress. When we use swing and VOLO model with 51.59 MIOU on test set and apply a model aggregation, the performance increased to 55.1. With extra dataset, test time augmentation, and the change of gamma, we finally get 58.06 mLU on test set. The result is tested in development phase. Let me make a summary. First, we achieved the third place in the challenge mainly based on the power of transformer model on large-scale datasets. We get the competitive results through the aggregation of transformer model. However, we think that still a lot of progress can be made. During the challenge, we set the aggregation parameter gamma as a hyperparameter. Maybe we can get higher score if gamma is produced by a trainable network. The most regretful thing is that we failed to leverage the temporal information in such a video dataset. We have tried TMANet and video swing transformer to extract the temporal feature, but we didn't get a better result than the result of models that directly process single frame. If a proper way of using temporal information can be adapted, maybe we can get higher score. Here's our references. That's the end of my introduction.